So our alkene this time reacting with an acid in aqueous conditions. Of course, aqueous conditions means that the acid can produce hydronium ions. Hydronium ions are a true source of acidity in aqueous solutions, ready to give away a proton. And it's giving away a proton to that electron-enriched alkene. Picking up the proton, and then the first step of the reaction, as the electrons revert back to the oxygen, produce water and a carbocation. Of course, this is a relatively slow step because of the high energy of that secondary carbocation. Now, of course, the water which is produced can act as a nucleophile and attack the carbocation, which is an electrophile. But we've got a substitution next door, and that substitution next door allows for the hydrogen to jump across, taking the electrons with it, to produce a tertiary carbocation. This is, of course, what we refer to as a 1-2 shift. So that tertiary carbocation is more stable than the secondary carbocation we originally produced. And now if we reintroduce the water again, it can attack as a nucleophile, attacking the carbocation, which is an electrophile, and we produce a new oxygen to carbon bond. This is going to be a relatively fast step for the reaction as we move towards the alcohol product. We've got a positive charge on the oxygen, so we need another molecule of water, this time acting as a base, picking off a proton from the oxonium ion as we move towards the production of that final product of the alcohol. Of course, this is a continuation of our fast step. And we finish with hydronium ions, just as we started with hydronium ions. So those hydronium ions are really catalytic in nature.